Substitutions. So suppose that p of z is a polynomial that has roots r1, r2, all the way up to rn. Now, obviously what I mean here is that these roots are the solutions to the equation p of z equals 0. Let's suppose that f of z is some invertible function, and alpha 1 is equal to f of r1, alpha 2 is equal to f of r2, all the way up to alpha n equals f of rn. Then, if we take the equation p of f inverse of z equals 0, then it must have roots alpha 1, alpha 2, all the way down to alpha n, because, well, p of f inverse of, say, well, alpha I is equal to p of ri, which is equal to 0 since ri is a root of that equation. Now what we're going to use this observation for is if p of f inverse of z is another polynomial, which sometimes it will be depending on what the function f is, then if we know a polynomial with roots r1, r2 all the way up to rn, we immediately can get a different polynomial with roots alpha 1, alpha 2 all the way up to alpha n. And here we see a nice example of it in exercise 1.7. We have the roots of the cubic equation 3z cubed minus 2z squared plus z minus 1 equals 0 are alpha, beta, and gamma. And then we want to find a cubic equation with roots 3 alpha minus 1, 3 beta minus 1, and 3 gamma minus 1. So clearly the function f we were talking about before is going to be 3 times z minus 1. And this is an invertible function because it is a line. And we have our polynomial p of z is equal to 3z cubed minus 2z squared plus z minus 1. And then we also have f inverse of z is clearly equal to z plus 1 divided by 3. And so if we consider p of f inverse of z, then we know, well, if we set this thing equal to 0, then clearly we're going to get an equation that has the roots 3 alpha minus 1, 3 beta minus 1, and 3 gamma minus 1. Because, for example, f inverse of 3 alpha minus 1 better be equal to alpha. So clearly the roots of this equation here are indeed 3 alpha minus 1, 3 beta minus 1, and 3 gamma minus 1. And then all that's left to do is observe we can actually change this into a polynomial. So p of f inverse of z is going to be 3 times z plus 1 divided by 3 cubed minus 2 times z plus 1 divided by 3 squared plus z plus 1 divided by 3 minus 1, just using function composition there. And then from here, all that's left to do is expand this thing out and observe that we get another polynomial of degree 3. Alright, so we still have 0 on the left-hand side. 0 equals 3 divided by 27 times z plus 1 to the power of 3, which is z cubed plus 3z squared plus 3z plus 1. Okay, minus 2 over 9 times z squared plus 2z plus 1. And then plus just, 1/3 of z plus 1. And then minus 1. Now let's multiply both sides by 27 just for convenience. So this is going to become 3. This is going to become 6. This is going to become 9. and this is going to become 27. Alright, and then we have 0 is equal to 3z cubed, and there are no other z cubes. Then we have 9z squared minus 6z squared, so that will be plus 3z squared. And then we have 9z minus 12z, so negative 3z, and then plus 9z, so that will be plus 6z. And then we have 3 minus 6 minus 27, so that will be minus 30. Whoops, my mistake, I also forgot the plus 9 here. So minus 30 plus 9, so that will be minus 21. And then from there we can divide by 3, so we get z cubed plus z squared plus 2z minus 7 equals 0. Be careful when you're doing these things. I'm being kind of lazy and not writing down very much here and trying to do too much in my head, which is why I made that mistake there. It's an easy way to lose marks, so I suggest when you're doing it for real in your exam, you include as many lines of working as possible, and that way you're less likely to make a trivial error like that.